Alright, so this is going to be a review of U-substitution, okay? So in general, guys, just keep in mind that if, remember that the derivative rules for the chain rule specifically, it says that if you're going to differentiate something that is a composition of two functions, then what you're going to get is you're going to get the derivative of the outer function with the inside left alone times the derivative of the inner function. So as a result, when you're trying to, you remember from the fundamental theorem that if I integrate this, then what I'll get is what I had originally. So that means that, remember, I'm going to have to integrate this, okay? And so the point I'm trying to get at is this. If you see the product of something and then the inside of its derivative, then that means that you need to use a U-substitution. The product of something and basically its derivative. That's the idea. If you see the product of something and its derivative, then that means you can use a U-substitution. Okay, so let me show you what I mean. Here's an example. The directions are all these are the same. Evaluate the indefinite integral. Okay, so let's look at this first one. The integral of x times the squared root of 1 minus x squared dx. Alright, so here's what I mean about product of something times its derivative. If you see this, the derivative of this is definitely going to involve just a single power of x, which is what this is. So that's what you're going to want to look for. Now, there's a couple of different ways that you can do this, okay? This first example, I'll show you like maybe a couple different ways. After that, I'm just going to kind of do it the way that I feel like is best for students. And when I say I think it's best for students, especially in Calculus 2, you're going to have so many different integration techniques that you're going to want to be able to kind of see if you can do a U-sub or not. You need to be able to kind of visualize, just see an integral and be like, oh yeah, I think a U-sub's a good candidate there. Okay? And I think what's going to help with that is doing it this way that I do it, because that way you can kind of see, oh, okay, exactly what needs to be there, and you're literally going to make replacements. It's not solving for, it's nothing like that. It's like you can see this part's the U, this part's the du, and you're literally visualizing a substitution as opposed to solving an equation and replacing and canceling and stuff like that. You know, it's a totally valid way. If you want to do it, it's fine. I'm just telling you I don't recommend it. I recommend trying to think about it, specifically if you have all these different types of integrals to deal with. I'd recommend you do it this first way. And that's what I'm going to do throughout the whole video. I will show, though, this first one a few different ways. Okay? Alright, so the first way is the way I recommend. So method 1. And so here's what I'm going to do. I'm going to rewrite this integral as the integral of the square root of 1 minus x squared times x dx. Okay? And I'm not going to show all these steps every time either. Okay? So then what you're going to need to do is you're going to need to try to use your substitution. We're going to try to pick all of that to be our substitution. Okay? Our new u. So we're going to let u equal 1 minus x squared. But that would imply then that du is equal to the derivative of 1 is 0, the derivative of negative x squared is negative 2x dx. So I'm looking at the differential. So that means, like, if I know what u is, then the differential of u, or du, is equal to negative 2x dx. You could think about it anyway. So that's differentials. If you need to remember how to do differentials, then you can review that in the text. Alright, so now, if we look here, we need a negative 2x dx. We have an x dx. The only thing we're off by is the negative 2. If you're off by a constant, you can fix that. So what we're going to do is we're going to say this is equivalent to the integral of 1 minus x squared and then times negative 2x dx. But look, I just put a 2 in there. You can't just do that. If you put a negative 2 in there, then that means you've changed the value of it. You've multiplied it by negative 2. So we have to put a negative 1/2 out there to balance it. And the reason I say that is because negative 1/2 times negative 2 is 1. Okay, so now what I've got is I've got negative 1/2 times the integral of, and then look, all of this becomes u, And then all of this becomes du. And so now you've literally transformed this thing. You've changed it from an integral involving x to an integral involving u. Okay, so it's no longer, you've changed the variable. It's no longer an x integral, it's a u integral. So now this one's pretty easy to deal with. You can just rewrite this as the integral of u to power 1/2 du. And so then this is negative 1/2 times u to power 3/2 over 3/2 plus c. The 2's cancel. You're left with negative 1/3 times u to power 3/2 plus c. What was u though? You have to back substitute. U is equal to this 1 minus x squared. You see, we were asked originally an integral about x, so we can't be like, oh yeah, u equals this. Or, you know, the integral is this stuff in terms of u. You have to give it back in terms of x. So remember, u is 1 minus x squared, so this now becomes negative 1/3 times 1 minus x squared, all to power 3/2 plus a constant. Okay, that's it. Let's do another one. Okay, how about this one? I have the integral of x squared times the sine of x cubed dx. Okay, so I'm going to notice, I know that when I differentiate something, the power gets knocked down by 1, so I know that the integral of x cubed is going to involve x squared. So I'm going to let u equal x cubed, and that would imply that the differential of u is equal to 3x squared dx. So I've got the x squared, but I need the 3. That means I need to put a 1/3 out here. So now I've got 1/3 times the integral of, and look, all of this becomes du, right? Because du is all of this, the 3, the x squared, and the dx. And you're going to replace that with the du, and then this becomes the sine of no longer x cubed, but sine of u. Okay, and so that's the idea. So I'll even do it this way. I'll highlight here. All of this together is du. Okay, and then, but yeah, so that's the idea. Okay, and then this over here was u. So now this is 1/3 times, okay, we know that the derivative of the cosine is negative sine. So that would mean that I would need to put a negative here, because now I know that the antiderivative of negative sine is the cosine, but if I put a negative there, I have to put a negative out here. And you can show that with an additional U-substitution, but I won't. So this is negative 1/3 times, and then I know, like I said, the derivative of the cosine is the negative sine, so that means the antiderivative of the negative sine is going to be the cosine. So this is the cosine of u plus a constant. I've got the negative third, so I'm good. You have to back substitute though. So the cosine of u, remember, was x cubed, and then plus c. Okay. Let's do another one. Okay, yeah, let's do another one. All right, so this is going to be number 3. All right, so here's one. You have the integral of, we've got 1 minus 2x all to power 9 dx. Okay, certainly you can span this if you like. I mean, that's going to be really involved though. You could even, I mean, even if you use the binomial theorem, you know, and use coefficients that are coming from Pascal's triangle, it's still going to be pretty involved. It's going to take a long time to expand the whole thing. So let's just use a U-substitution. So we're going to let u equal 1 minus 2x. That would imply that the differential of u is equal to negative 2 dx. So I've got the dx, I just need the negative 2, but then that means I'm going to need a negative 1/2 out here. And so now this is equal to negative 1/2 times the integral of u to power 9 du. No problem. So this is now negative 1/2 times u to power 10 over 10 plus a constant. So then you're just going to rewrite this as negative 1/20 times u to power 10 plus c, but then what was u? U was 1 minus 2x, so this is now negative 1 over 20 times 1 minus 2x all to power 10 plus a constant. Okay. Let's do another one. Number 4. Number 4 says the integral of the sine of t times the square root of 1 plus the cosine of t dt. Again, I'm looking for the product of something and its derivative, or at least an inside function. I want to see a f composed with g, a composition, and then the product of that composition with the derivative of the inside. So it looks to me like this is going to be my u, and then my du is going to involve this. Maybe I'll have to fix it up with a constant or something, but that's the approach I'm going to take. So let's let u equal 1 plus the cosine of t, but that would imply then that du is equal to, the derivative of 1 is 0, the derivative of the cosine is negative sine of t, and then dt. Okay, so now here's what I'm going to do. I'm going to put the negative here, and then the negative outside. And so now I've got this negative sine of t dt, so that's all going to become du. So I get negative the integral of the square root of u du. So this is equal to negative the integral of u to the power 1/2 du. Now you're actually going to integrate, so we get negative u to the power 3/2 over 3/2 plus a constant. So the u is equal to 1 plus the cosine of t, so this is negative 2/3 times 1 plus the cosine of t to the power 3/2 plus constant, and you're done. I forgot earlier, I told you that I would go through it a couple of different ways, and I forgot after the first one. So here was method 1, which I've been using now. Here was a second method. If you'd like to do this, you can. And there's even variations beyond these. Alright, so let me go back through this first one again. We have the integral of 1 minus x squared, it's the square root of that, and then dx, or times x dx. Right? Okay, so here's what you could do. You could let u equal 1 minus x squared, and then that would imply that du dx is equal to, so the derivative of 1 is 0, the derivative of negative 2x is negative, the derivative of negative x squared is negative 2x. Okay, and then I've seen people solve for dx then. So that means that you're going to solve for the dx. So this is du is equal to negative 2x dx, and then divide both sides by negative 2x. So this becomes negative 2x, and so then now we know that dx is equal to du over negative 2x, which is fine. Now replace that. So this is the integral of the square root of 1 minus x squared times x times, and instead of writing dx, now I'm going to write du over negative 2x. And then now what's going to happen is this x is multiplied, because that's x over 1. I know I've written it kind of low, but this is x over 1. Okay, so that x and this divided by x is going to cancel, and you're left then with the integral of the square root of, you can call that u, and then we have the du over negative 2, and then that negative 2 can come out as a negative 1/2, because it's a negative 2 in a denominator. So this becomes the square root of u du, and then you're just going to say, okay, that's negative 1/2 times the integral of u to the power 1/2 du, which that's going to be negative 1/2 times u to the power negative 3/2, or I'm sorry, u to power 3/2 over 3/2. The 2's cancel, you're left with negative 1/3. And then u, which was the 1 plus, it was 1, oh, it's 1 minus x squared to the power 3/2 plus a constant. Okay. You're still going to get the same thing we got over here. And it's fine. It's nothing wrong with it. There's other little variations. You just have to make sure before you integrate everything, you have to get everything in terms of u or du. You cannot have any x's. I don't almost like it a little bit because I think I've seen people try to proceed where they have both variables, an x and a du, because they don't understand. They lack understanding. So I think with this, it's nice because you get to see everything just disappears at once and it gets replaced. It transforms from an x integral to a u integral. But again, it's style. You know, it's really just a stylistic issue. I think that it's easier for students. That's my theory. I don't necessarily have really any proof of that, but that's my opinion on it. So I'm going to focus it on this way because I feel like it's best for students. It might not be the easiest thing to understand at first, but I think it's going to be the easiest thing to understand in the long run. Okay, let's do a few more. Let's see, I already did that one. Okay, I did 4. Okay, so let me do number 5. So I've got the integral of the sine of 2 theta over 3 d theta. All right. So same kind of deal. I'm going to let u equal 2/3 theta, but that would imply that the differential of u is 2/3 times the differential of theta. So then I'm going to put a 2/3 here, but then I've got to put a 3/2 here to balance. So then I've got a 3/2 times the integral of the sine of u du. I know that the derivative of the cosine is negative sine, so I'm going to put a negative sign here and a negative sign there. So then I've got negative 3/2 times the derivative of the cosine is negative sine, so the antiderivative of negative sine is the cosine. So this is the cosine of u plus constant. Okay. And then you got a back sub. So you've got negative 3/2 times the cosine of, and this is 2 theta over 3 plus c. Now I'm just going to say this, okay? I've seen people try to get creative and make up rules that don't actually exist, and they'll pull out this 2/3, they'll pull it out, even though you can't do that. There is no law that says you can do that. Constants can't come out of functions. You can pull them out of integrals as constants, you can pull them out of derivatives as constants, you can do the same thing with limits, but you can't just pull them out of functions. There's no way. I mean, if that was the case, we wouldn't need the double angle formula, we wouldn't need the half angle formula. I mean, like, we wouldn't need like a lot of different things. Trig would be considerably easier. Also, things wouldn't work the same way, and I mean, the laws of mathematics and physics wouldn't be the same, you know. So anyway, you can't just do that. So don't try to make up stuff that doesn't exist. Okay, be careful. Now, in truth, also, one other note, you know, in theory, you should have parentheses around this, in which case this negative 3/2 would have to distribute to that c, but then 2/3 or even negative 2/3 times that constant is still just another constant, so we typically just write it this way, and that's sufficient. Does it sort of blister the distributive law? Yeah, a little bit, but does it matter because it's constant? No, it doesn't matter. Mathematically, it's the same, so typically we just leave it alone. There was one other thing I was going to say. What was it? It was something... I brought up the thing about the constants, and there was something else I thought related to that. Something. Well, just in general, kind of just be careful, guys. Make sure you don't just start making up rules. That's kind of it. It's kind of a big deal. All right, so this is number 5, I guess. All right, this is number 6. All right, number 6 says I've got the integral of the secant squared of 2 theta d theta. Okay, so same deal. I'm going to have to substitute. Oh, yeah, I remember what I was going to say. It never, ever, 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 ever makes sense to let u equal x or let u equal theta. Ever. Never. Ever, ever, ever. Okay? You would never just let u equal x or let u equal theta or something like that, u equal t. You're never going to just let one variable equal another variable with nothing else. Because if you do, all you're doing is changing the symbols then at that point. You're not helping your problem. You're not moving the cause forward. You're just spinning your wheels. Do you know what I mean? So you're never going to want to do that. It doesn't make any sense to do that. Okay? Now, you can let, like u equal x plus 1, or you can let u equal like 2x or something like that. Then that's fine, because then you're doing something a little extra. Okay, here we're going to let u equal 2 theta, but that would imply that the differential of u is equal to 2 times d theta. So that would mean, okay, I've got the d theta, but I need the 2. That means I need a 1/2 there. So now this is equal to 1/2 times the integral of the secant squared of u du. Now the derivative of the tangent is the secant squared, so that means that the antiderivative of the secant squared is the tangent. So this is equal to 1/2 times the tangent of u plus constant. Okay. Let's do another one. Number 7. Okay. Okay, this is a good one. This is a very, very good one. This kind of freaks people out. The integral of the secant of 3t times the tangent of 3t dt. Alright, I know that the derivative, okay, so first let's make a substitution. Let's let u equal 3t, but that would imply that du is equal to 3 dt. So I'd need a 3 here and then a 1/3 here. Now I can rewrite this as 1/3 times the integral of the secant of u times the tangent of u du. All I was going to say here is that sometimes this messes people up because like they see the product of two functions and they get kind of confused and stuff. Just remember that the derivative of the secant is the secant times the tangent. So that means the antiderivative of the secant times the tangent is just going to be the secant. So this is equal to 1/3 times the secant of u plus constant, and we're done. Oh, no, you got to back up. U is 3t. So this is equal to 1/3 times the secant of 3t plus constant. Okay. Oh, I think this last one I left is u. You can't do that either. Okay, that's not done either. So this is equal to 1/2 times the tangent of, don't forget to back sub, 2 theta plus constant. Okay, that was the last time I did that, I think. Okay, number 8. Alright, so we've got this one. This is the integral of y squared times. We've got 4 minus y cubed, and it's all to the power 2/3 dy. Okay, well what we're going to do is we're going to let u equal 4 minus y cubed. That would imply that du is equal to negative 3y squared dy. So what I'm going to do is I've got the y squared, I've got the dy. I'm going to put a negative 3 there and then a negative 1/3 there. So now I've got negative 1/3 times the integral of, and you've got 4 minus, or I'm sorry, so the 4 minus, okay, let's kind of look at this carefully. This part is u, and then this part here is du. So that now this is the integral of, this is negative 1/3 times the integral of u to the power 2/3 times du. So now this is negative 1/3 times, and you've got u to power, so you've got to add 1, so 5/3 over 5/3, so these are going to cancel, and then plus a constant. So now what you've got is you've got negative 1/5 times u, but u, remember, is 4 minus y cubed to the power 5/3 plus c. Okay. Okay, let me do some that are, let me do this one that's kind of interesting. Alright, so this is number, what was the last one I did? 9. Okay, so I've got here, this is the integral of the sine of x times the sine of the cosine of x dx. That looks pretty tricky. Tricky. Alright, but that's okay. Let's see here. I'm going to let u equal what? Well, this is the function that's inside something else. You know, this is a product. Okay, that's fine, but you got to pick the inside function, okay? So that's going to be the cosine. So u is going to equal the cosine of x. That would imply that the differential of u is equal to the derivative of the cosine is negative sine, so negative times sine of x dx. That means I need to put a negative here and a negative there, and then I've got negative sine of x dx. Okay, so that's great. So I get negative 1 times the integral of, and I've got du times the sine of u, right? And so then this is equal to negative 1 times, and then, yeah. So now the derivative, okay, so this negative, I'm going to bring this in really quick for a second. And then the derivative of the cosine is negative sine, so that means that since this is the antiderivative of negative sine, I'm going to get the cosine of u plus a constant, but then that u is equal to the cosine of x. So this is equal to the cosine of the cosine of x plus constant, and that's it. Alright. So, I mean, there's a lot of other problems you guys can review in your text and stuff. These are all good problems, so you really want to make sure that you're very, very, very comfortable with U-Substitution, especially if you're in Cal 2, because you're going to be doing a whole lot of additional integration techniques, and this is kind of the only big deal that you know. In Cal 1, I mean, you know how to split an integral with addition and subtraction, you know how to pull constants out, and then you know like the power rule. But aside from that, I mean, this is kind of like the only other thing that you know. But in Calculus 2, you've got like tons of rules, so you've got to be careful. Okay.